Welcome back to Python tutorial 2. We have presented how to represent a wave function, how to discretize a wave function, or how to represent a wave function on a grid, position grid. And next what we will do, we will take that discretized wave function and we will normalize it, and we will check how to normalize it. The wave function which we have taken, this is the form of the wave function we have taken. Clearly it is not a normalized wave function. I can prove that, and in order to prove that, what I need to do is that I have to take this integration minus infinity to plus infinity. Remember, it's an analytical way of doing normalization, and numerical way of doing normalization we will find out very soon. So we have to take the square of absolute value of this wave function and then take the integration of it. This integration is going to be then minus infinity to plus infinity e to the power minus 2 x square dx. This is nothing but square root of pi by 2. This is the standard Gaussian integral which we have been using in this course in many occasions. So normalized, if it is a normalized wave function, then this integration should have given me 1, but because it is not giving me 1, it is not normalized. So I have to make it normalized, and for the normalization what I do, what we will do is we have to find out the norm. Norm is defined by the square root of this entire integration, the square root of this integration. And once we get the norm, then we divide the wave function, non-normalized wave function which is not normalized yet. That wave function has to be divided by its own norm to get the normalized wave function. And then if I do minus infinity to plus infinity integration psi normalized, this should give me 1. So that's the procedure for doing normalization. So let's look at this. For this wave function, we can easily find out the norm. Norm is going to be square root of this. So I have this pi by 2 already. So norm is going to be pi by 2 to the power 1 by 4. So analytical form of normalized Gaussian function. So this is the Gaussian function. So normalized Gaussian function would be given by, we have to divide it, so divide by the norm. So it is e to the power minus x square, this is the function, and I am dividing by norm which is pi by 2 to the power 1 by 4. So this is nothing but 2 by pi to the power 1 by 4 e to the power minus x square. That is the normalized Gaussian wave function. And what is our task here in this module, in this tutorial, is that we normalize the discretized wave function. This wave function has been discretized already. We have seen how to discretize this wave function. We will use that discretized wave function and we will numerically normalize it. So there are and in order to do this normalization, clearly we have to do this numerical integration, because this integration has to be now performed numerically. This integration will give me the norm, and once I get the norm, I can take square root of that norm and divide this wave function by the square root of norm. I get the normalized wave function. So ultimately we have to depend on numerical integration of this absolute square of absolute value of the wave function. Now there are many ways one can perform numerical integration. Numerical methodology can construct a full-fledged course, and we we are not in this course, we are not actually going over numerical methodologies. We are always making use of SciPy, all the functionalities which is implemented in SciPy, because SciPy has been developed keeping scientific community in mind, and there are many protocols which is already packaged in SciPy, which can be very useful for the numerical analysis or numerical solutions. So, we'll make use of a highly optimized integration package of SciPy. It is called SciPy Integrate. This package provides many options to do numerical integration. So, it has a pre-written code in it, and we are going to use that code directly to perform this numerical integration. The SciPy Integrate submodule of SciPy provides a number of integration techniques, including Simpson's rule. Now, what is the Simpson's rule? We will not go over in details in this course. It is a technique, numerical technique, which can enable one to get a numerical integration done. So, we will use this Simpson's rule. There are many other techniques which can be used, which are already included in this SciPy Integrate package, but we are just selecting Simpson's rule. And the construct which we have to use in order to implement this Simpson's rule for the integration, numerical integration, is following. It is Sims yx functionality, where y would be an array and x would be also an array. Both would be an array, and we have already got those arrays. We instead of y, we have now x. That is instead of y, we have now this psi x square of the absolute square. This is going to be my y array. This is going to be my y array, and x array is already the x grid we have prepared. So, already we have both arrays in hand, and we have to use that under this construct Sims yx. Just we remind ourselves that when you have used plot functionality of pyplot, we have used xy, plot xy construct. And here, when you are doing numerical integration imported from the module imported from SciPy Integrate, I have Sims yx. So, y comes first and then x. So, this is something which may confuse suddenly somebody if you are doing this Python programming for the first time. Just remember that we have already used plot functionality or pyplot that has a construct xy, but here I have a construct yx. So, do not get confused or do not shuffle these two arrays or do not write like Sims xy. Don't like it. Don't write it like this way. So, this is just something which we may do something wrong in the coding if we write it. So, this Sims x or the Sims yx functionality of SciPy Integrate submodule integrates the y array numerically, while x array provides the points at which y has to be sampled to compute the Simpson's rule of the numerical integration. So, we will use this. It is a very simple thing, and it is a pre-written code it has. So, once you invoke this Sims functionality, it is actually using that pre-written code in Python SciPy Integrate submodule, and it will give me the result. So, what we will do here in our present problem, square of absolute value of y function. This is the y array, as I have told before, that this is going to be my y array. Is a square of absolute value of the wave function, this wave function. This is nothing but the probability density. This is the probability density function we are familiar with. This is called probability density function, which is square of absolute value of the wave function. And this y array has to be integrated. The probability density function is sampled at the points present in the X array, and X array we know that it is, we have defined as minus 100 to plus 100. So it is the X grid, and because we are taking X grid to be minus 100 to plus 100, remember in this integration we have limit minus infinity to plus infinity, and we will not be able to use this limit clearly. What we will use, the moment we use this Sims functionality of this psi pi integrate submodule, it will adopt the limit of the X grid, which is minus 100 to plus 100. So now this is my practical numerical calculation, which is going to be performed with the help of Simpson's rule. Now Python's built-in functionality, this ABS, absolute value, ABS will give me returns absolute value of a given number, and that exactly what we need, because this is absolute square of absolute value of the wave function. And I can get this absolute value of a wave function by this ABS, which means that I have to write ABS within bracket psi x. Then I get the absolute value. So what does it mean by absolute value? If the number is a complex number, let's say a plus ib, if it is a complex number, then ABS will return its magnitude, which is a square root of a square plus b square. I will get this value. And if the number is a real number, if it is a real number, for a real number, ABS functionality, this functionality is actually present in Python's built-in library. It does not need to be imported from other module. So this, if it is a real number, then it will remove the negative sign of the number. It will remove the negative sign of the number, and that is the way it will return. So what we need to do is that we have to use this absolute value of x, psi x, and then we have to do the integration, make it square and then do the integration. So we will now numerically implement this idea. Clearly minus infinity to plus infinity is not the limit. For us it is going to be minus 100 to plus 100 limit. The limit has been, will be automatically selected in the Sims. If I use Sims functionality, this is y, then x, then x grid limit would be selected as the limit for the integration. So we will see that the first two lines are importing the libraries. Then we have to definitely create the x grid. Once we have created the x grid, we have to discretize the wave function. We have already seen how to do that. Then these are the new steps for the normalization. And this is very simple 3 steps normalization steps. First we will define the probability density of psi. how we are going to define? It is nothing but absolute value of psi square. So so this part is nothing but psi x square. That's the probability density. And then we have to find out the norm. Norm is going to be square root of this integration of this probability density versus x. So we have different, this is my y array, this is my x array. So I have to first integrate it, and after the integration I have to take the value, square root of that value, and then we are going to print the norm. We will just double check what is the norm we are getting. So we will move to laptop, and we have these libraries, importing the libraries. We are going to keep it as it is, but the plotting part we do not need because we are not going to plot it anymore. Instead of plot, we have to import the sims functionality from SciPy integrate submodule. So I'll write down from SciPy dot integrate import sims, so that I can use that later. So this part remaining to be the same because we are creating the X grid first, then we are discretizing the wave function, then this plot part we do not need anymore. We have to now, after discretizing the wave function, we have to now calculate the norm. And how do I calculate it? First I have to get the probability density of psi. So probability density, prob density, I'm just giving a name with underscores so that anybody can understand it when it's reading it later stage. So using a good name of a particular function can help understand what is the meaning of that function. So that's the reason I'm explicitly writing like this way. Otherwise one can use also y to represent the probability density function. So probability density function, what does it mean? It is the absolute value. First I have to take the absolute value of psi. So this is going to give me the absolute value of psi, which is another array basically. It will take absolute value of each point, each element of psi, and then this needs to be, I have to take the square of that value, each value. So so probability density gives me another array where each element, where we have taken absolute value of each element in the array and then we have squared it. So norm would be defined by square root, but we haven't imported square root. Square root is not a this mathematical function, square root mathematical function is not available with Python's built-in library. It has to be imported from SciPy. So you will be using sqrt. Remember, many of these functionality can be imported from NumPy as well, but we are deliberately not using NumPy at all. We don't want to mix up the libraries. We want to just keep things simple. That's why we are using always this SciPy module, because it is more optimized, and we'll keep using the same module for different purpose. So norm I have to define by square root of the integration of this function. So I will use sims, then I have to use y comma x. X is already defined, and then I have to use print to check what is the norm I get. Okay, so we have we have to check when you are using many brackets, we have to always think, we have to double check whether the brackets are in proper order or not. We have 2 brackets here, so we have 2 brackets here also, and that exactly what we need should always double check. So if we run the program right now, then we get back the norm. Norm is 1.119. We go back to the slides, we get this value for the norm. This is nothing but the value which we have used before. We analytically solved the problem and we have found that the norm has to be pi by 2 to the power 1 by 4. So this is the value which we get here numerically. We will move on and we will once we have understood that we have been able to get the norm, remaining part is very simple. We have to just divide the wave function by the norm and we get the normalized wave function. So this part for the normalization is quite understandable. Up to this far we have understood how to get the norm, and then we have to name another, we are giving a name PSI norm, which is normalized wave function, which is nothing but the earlier wave function PSI. This is the earlier wave function which was not normalized. I am now dividing by the norm and I should get the normalized wave function. So what we have done is that to make sure that we have normalized it, we can always double check by taking this integration one more time. Psi, if it is a normalized wave function, then this is going to be 1. So we are doing one more time. We are taking this as a wave function, normalized wave function, and checking whether we are getting norm to be 1 or not. So these 3 steps has been written to recheck whether we have got the normalized wave function. So for that we have to again take the probability density, then the integration, and then square root of that integration is going to be norm, and I am going to print norm. So we will move to laptop and we will just we do not need to print the norm anymore. We will just keep the norm, and then we will just normalize the wave function. We can normalize the wave function by writing PSI norm. This is a new name we are giving, which is nothing but PSI divided by norm. So I have this normalized wave function. Remember, PSI norm is still an array. It has 2001 number of points, and this is representing an array. So PSI divided by norm, it means that each element of PSI has been divided by the norm value. Once we get that, then we will recheck whether we have really normalized the wave function. For that, we will define the probability density of this normalized wave function. We are giving the pattern of naming, we are keeping similar, probability density PSI norm. So this is going to be absolute value of this normalized wave function. What it does, it will take the absolute value for each element of this array and then square it. So this is again another array we have prepared, and then I will write norm 1. This is going to be then square root of here PSI norm. So Y array is going to be PSI the probability density of PSI norm, and then if I want to print I will write down. So, I execute the program. What I get back is 0.999, which is equivalent to 1. So, I will go back to the slides. So, I have this value which is equivalent to 1. So, this kind of floating point value will make it depending on, because it is a numerical integration, we may not get 1, but 0.999 is equivalent to 1. So, because it is 1, the norm is getting 1, it means that the wave function which I have right now here, the PSI norm, this PSI norm is now a normalized wave function that we have proved. And always in quantum dynamics, we have to always use a normalized wave function. This is something which we have learned in this course. We will move on and we will look at the expectation value of position. Now, expectation value of position, what does it mean? I will just remind. If I have a probability density distribution which is psi x absolute square, if I have this, then question is what is the mean of this or average of this distribution? So, clearly for Gaussian probability density distribution, the mean would be here. This is called the mean value. And what does it mean? Experimentally, it means that it's the average of many repeated experiments. That's the average value. So, expectation value has a direct connection to the experimental outcome, because in the experiment we repeat the experiment many times, and after repeating it, if we take the average of the outcome, we get the value. That value should correspond to this expectation value, which can also be calculated from the known wave function of the system. So, that is the basic idea. Expectation value of position of is given by this. In general, it is given by, if x is an operator, then expectation value is going to be minus infinity to plus infinity, then psi star x, then x operator, then psi x dx. That is the expectation value, which can also be written, because x is an position operator is nothing but a multiplication operator. One can keep it anywhere in the integrand. Its position does not mean anything, because it is multiplication. Multiplication does not follow any order. It can be multiplied by this way, it can be multiplied by this way. Both sides is perfectly fine. So, but operators, in general, operators does not work that way. If we consider the derivative operator, if I have y z, then this derivative operator is acting only on z, it is not acting on y. So, operator in general has a particular direction, but position operator, because it is a multiplication operator, it does not have any direction. So, one can position it anywhere. So, I have positioned it here, so that I can club this psi star psi together, and psi star psi is nothing but the absolute value. So, in the end, expectation value, if we want to calculate, all we need to do is that we have to construct another function. What is that function? The first function is the probability function, which is psi x absolute value square of absolute value of psi x. This is one function. It has to be multiplied by x. The x is another function. So, these two functions needs to be multiplied. Now, if we think about this, probability density distribution looks like this, and x has x function. This function has certain way. Let us say this is the way x is working, and if we multiply two functions, let us say these two functions are multiplying, in terms of matrix or in terms of this discretized on a grid, it is nothing but multiplying each element. If it is a simple multiplication, scalar multiplication, then it is multiplying each element to get the final form of the total function. So if I multiply, so this element has to be multiplied by this element, and each element will be defined by its own grid point. So for corresponding to each grid point, I have two elements for coming from two functions, and they needs to be multiplied. So each element has to be multiplied. So it's a element wise multiplication because it's a scalar multiplication. And scalar multiplication, so it's very easy to do, and so in the end this is an array which will be represented by like this way: psi x naught square, then x naught, then psi x1, then x1, psi x2, x2, like this way we continue. And x naught is the grid point. So initial grid point was x naught, final grid point was xn minus 1. So these are the points we get in the probability density distribution. So this is the array we create by this multiplication, and this is the array which we will be using for the integration of Simpson, following the Simpson's method as an Y array. So, but the question is, in Python programming, the scalar product of two arrays is given by element wise multiplication, and element wise multiplication can be done by just multiplication operator, which is available in Python's built-in library. So if I have Y array and X array, if I multiply, then what will happen? It will do element wise multiplication. Each element will be multiplied by the corresponding other element. So y1 will be multiplied by x1, y0 will be multiplied by x0, then y2 will be multiplied by x2, and so on, and then it will give me another array. So it's very simple. So we'll move forward and we'll see how to get this integration done so that I can get the expectation value. This is the integration, and again practically we cannot do this minus infinity to plus infinity integration. This is going to be done with the help of Simpson rule, and for that it will just pick up the integration limit as the x grid limit. So this is going to be our integration. This entire part is going to be y. So in the Simpson rule I have to specify y, and y is going to be this part, and x is the x grid. Over the x grid it will be sampling the y values and then integrate it. This x grid creation part is known to us now. Discretization of the wave function is known to us. Then calculating the norm, we have to first normalize the wave function, because this expectation value, this when we write down minus infinity to plus infinity, psi star x psi dx is the expectation value. We assume that psi is normalized. So we have to first normalize the wave function to get the right expectation value. So we normalized it. This part is also known, and then little bit tricky we have made here. First we have to get the probability density of the normalized wave function. That is known to us now. Then the integrand part we will just write down. This is the integrand part. So what we have done here, this probability density will be multiplied by x. We get the integrand, and then expectation value is going to give me the integration part, where y is this entire integrand, and then we'll print the expected value, expectation value for this. So this part is little new, others are known to us. So we'll move to the laptop and we'll write down the program. We have everything remaining to be the same, then except for this is X grid we have prepared, then discretize the wave function, then we have to normalize the wave function. This far we are done, and then we have to find out the expectation value of the position. So, this part will be deleted and we will write down finding expectation value of position, where first we have to write down this probability density PSI norm, which we need to do, because after we normalize it we have to find out the probability density, and then this probability density has to be multiplied by x, so that I can create another we multiply by x, and then expectation value is expectation v, expect v, which is representing the expectation value. Expectation value we get from this integration, and in this integration y has to be this integrand. And then we are going to print the expectation value. So, if we execute the program, we get minus, we go back to the slide, we get minus 6 multiplied by 10 to the power minus 18, which is almost equal to 0. It is the 0 position, and that should be because e to the power, our wave function was e to the power minus x square. This is a Gaussian function which is centered at x equals 0. A Gaussian function which is centered at x equals 0 is having this form. But if I want to change the Gaussian function to be centered at different place, then I have to write x minus a whole square. If I do that, then Gaussian will be centered at position A, and that will prove here. We will move to laptop. I will just change this the definition of this Gaussian function. According to this definition which I have used right now, this is centered at x equals 0. Now, I will center it at x equals, let us say 3, x minus 3, that is why I am writing. And once we do that, then we will see that we will check what is the expectation value we have. Expectation value we get 3.000, which is close to 3. Numerically we get some error always, and we have to deal with this kind of error, but this is 3 we are getting. So, basically what we are seeing is that center of the Gaussian is representing the expectation value of the position, and that is now 3. If I change 3 to 10, I will see that expectation value I will get 10. Instead of 10, I get 9.999, which is equivalent to 10 numerically. So, what we see here is that for a Gaussian function, the center of the Gaussian is actually represented by the expectation value of position. That we have seen before also, and one can do analytically, one can perform analytical integration for this with the help of this kind of function to check whether really expectation value would be at this value, this at this parameter which we are using. So, we have come to end of this course end of this module, this Python tutorial 2, where we have learned how to represent the wave function in the computer programming with the help of Python, and then how to normalize the wave function. That is a very important step, because in every quantum dynamics problem we'll be normalizing it, and first we have to normalize it, and then we have to move forward, and then we have learned how to get the expectation value. We will stop here, and we will continue learning time dependent quantum chemistry in this course in the next module and next tutorials.